In this video tutorial, I am going to discuss about allosteric regulation. Remember, not all the enzymes are subject of allosteric regulation. Instead, there are only some specialized enzymes which can undergo allosteric regulation. Such specialized enzymes are called as allosteric enzymes. Now, this allosteric enzyme, on their surface, they have one very specialized site. It is called as a allosteric site. Remember, this allosteric site is other or different than the active site. So, allosteric site and active site both are different. Now, on the surface of allosteric enzymes, there can be one or more allosteric site. Okay, so there can be 2, 3, 4, 5, this many allosteric sites can be present. The second important aspect is that allosteric enzymes chemically they are oligomeric in nature. That means there is presence of one or more subunits. If all the subunits are identical, then they are called as a homomeric, and if the subunits are different, then it is called as a heteromeric. Now let's try to understand about these allosteric enzymes more with the help of illustration. So for that, suppose this is the allosteric enzyme. Allosteric enzyme. Now as an example of allosteric enzyme, I had chosen this oligomer which has two subunits and both subunits are identical. So this example, it represents homomeric having two subunits. Right. Now we know that on the surface of all the enzymes, there is a presence of active site. So let's say this is the active site of the enzyme. And we also know that allosteric site is different than the active site. So let's try to show allosteric site. So this is the allosteric site. We also know that allosteric site can be more than one. So let's show two allosteric site. One is this and second one is this one. Now, as I told you earlier that this example, it represents homomer. So that means this second subunit is identical to this first subunit. So that means all these three sites will be present on this subunit also, right? So let's say this is the active site, this is the allosteric site, and this is the other allosteric site. So this is the allosteric site. Remember, all these pits shown in the red, these all are allosteric sites. So in this example, we have total 4 allosteric sites. Now with these allosteric sites, there are certain molecules which can bind. So let's say with this allosteric site, this molecule binds, and with this allosteric site, this molecule binds. These molecules which can bind with the allosteric site, they are called as allosteric modulators. They are also called as allosteric effectors. So there are two names for such molecules. Now what happens? Allosteric modulator initially binds with this allosteric site, and this binding, so first they binds with enzyme and at the allosteric site. This binding will lead to conformational changes in this enzyme. So binding with the enzyme, it leads to conformational changes in enzyme, and because of this conformational changes, this enzyme's activity, it may increase or decrease. So that means there is a change in enzyme activity. So this change, it can be of two types. It may lead to increase enzyme activity, or it may lead to decrease enzyme activity. If this increased enzyme activity is observed when some allosteric modulator binds, then such allosteric modulators, they are called as a positive allosteric modulator. This positive allosteric modulator, they are also called as a allosteric activator. Whereas when particular allosteric modulator binds with the allosteric site and it leads to decrease in the enzyme activity, then particular allosteric modulator, they are called as a negative allosteric modulator. which is also called as a allosteric inhibitor. Now, this change in the enzyme activity, whether it can be increase or decrease, but we can change enzyme activity by one of two different ways. The enzyme activity can be changed by either changing the Km value or by changing the Vmax value of the enzyme. So if particular enzyme's activity is being changed by change in the Km value, then that particular allosteric enzyme is called as a K class of allosteric enzyme. And if particular enzyme's activity is changed by changing in the Vmax value, then particular enzyme is called as a V class of allosteric enzyme. So remember, this K class and V class is the type of allosteric enzyme, whereas this positive allosteric modulator and negative allosteric modulator, they are the type of allosteric modulator. Now regarding allosteric sites, if this allosteric site, it is able to bind with the positive allosteric modulator, then particular allosteric site is called as a activator site. And if allosteric site is able to bind with the negative allosteric modulator, it is called as a inhibitor site. So this activator site and inhibitor site both are the types of allosteric site. So once all of this terminology is clear, then we can move forward. Now we can discuss about the next important aspect of allosteric enzyme. Allosteric enzyme can exist in two different forms. One is the tight or taut form, where enzyme molecule is tightly packed. It is also called as a T form or T state. Okay, and this tight form is less active form of enzyme, whereas the other form is the relaxed form of enzyme. In the relaxed form, enzyme molecule is somewhat relaxed. It is not tightly packed, and it is also called as a R form. And such relaxed form of enzyme is actually a more active form of enzyme. Let's try to represent both of this form in a schematic manner. So just like before, suppose this is the allosteric enzyme in the T form. So here the enzyme molecule is tightly packed. Suppose this is the active site and this red represents two different allosteric site. Now to represent its relaxed form, we will relax this square little bit. So this relaxed square, it represents R form of allosteric enzyme, right? So here also this is the active site, this is the active site, and these are the allosteric sites. So remember, both of this form, it is a different form of same enzyme. Okay, so this active site and this allosteric site are same as of the T form. But what happens? This both forms are at equilibrium. For any allosteric enzyme, this T form and relaxed form both are at the equilibrium. Suppose, just as an hypothetical example, we have 100 molecules of this allosteric enzyme. Then it is possible that 50 enzymes are in the T form and 50 enzymes are in the R form. Now let's suppose that this allosteric site is a positive allosteric site, that means activator site, and let's say this allosteric site is a inhibitor site. Okay, so what happens if this particular allosteric modulator, it binds at the active site? So obviously enzyme activity will increase, right? So what will happen when this allosteric modulator, and obviously as it is activating the enzyme, we call it as a positive allosteric modulator, right? So when this positive allosteric modulator binds at this allosteric site, what will happen? It will convert this T form into the R form, which is more active, so enzyme activity increases. So allosteric activator, or it is also called as a positive allosteric modulator. Okay, so what will happen? It will convert T form into the R form. So now new equilibrium between this T and R form will be established. Let's say that by this allosteric activator, 20 molecules are getting converted from T form to R form. So 50 minus 20 will lead to 30, and 50 plus 20, it will lead to 70. So now more enzyme is available in the R form, so there will be more activity of the enzyme. The reverse will occur when allosteric inhibitor is present. And let's say, suppose this rounded allosteric site is an inhibitor site. Okay, so what will happen when allosteric inhibitor is present? So allosteric inhibitor binds over here and it will convert this relaxed form into the tight form. So let's say allosteric inhibitor is converting 20 molecules from the R form to the T form. So 50 minus 20, that makes it 30, and 50 plus 20, that makes it a 70. So now more enzyme is in the T form, which is less active. So that is how activity is decreased by the allosteric inhibitor. Now there is one more aspect, and very interesting one. It is what the substrate will do. See, whenever substrate binds at the active site, it always favor its R form, which is more active. So if you go on adding a substrate in this allosteric enzyme, what it will do? It will convert T form into the R form. So substrate works like a allosteric activator. The only difference is that substrate binds at this active site, not at the allosteric site, right? So remember, as a summary, allosteric activator and substrate both favors this more active R form, whereas allosteric inhibitor, they favors less active T form. So from the other angle, you can say that substrate binding favors more substrate binding, right? See what happened. Suppose here the substrate binds. So what will happen? Now this enzyme will be getting converted to the more active R form. So now this other active site, it will bind with the more substrate, right? So substrate binding favors more substrate binding. And this is called as a homotropic effect. Homotropic effect. Right? As the same thing is favoring its own binding, right? And it is going to be always positive, right? Whereas in case of allosteric activator or allosteric inhibitor, what is happening? This allosteric activator or allosteric inhibitor, they are changing the binding of the substrate, right? So here other molecule, not the substrate itself, rather we can collectively call this as a allosteric modulators binding influences substrate binding, right? Suppose allosteric activator is there, then more substrate will bind. If allosteric inhibitor is there, less substrate will bind, right? So allosteric modulators binding, it influences the substrate binding. So it is called as a heterotropic effect. And this heterotropic, it can be positive or negative. Whereas in case of homotropic effect, it is always positive. Now this phenomena from the different angle, it can be called as a cooperativity. What does it mean? See, if one substrate binds, then the second substrate binding will become easier. Okay, so we can say that first substrate is cooperating with its next substrate. So that is a cooperativity. And in this case, if we draw a diagram or a graph of velocity, that is V0 versus substrate concentration, then we can see such sigmoidal shape of graph. Now why sigmoidal shape graph is seen in case of allosteric enzyme? See what happens. Initially, when you go on adding a substrate concentration up to certain point, let's say up to this point, this much substrate concentration is increased, and simultaneously this much velocity is increased. But we know that one substrate binding, it favors more substrate binding. So what will happen? That after certain point, if you go on increasing the substrate concentration up to this point, then how much substrate concentration is increased? This much, which is slightly larger than the earlier phase. But see on the magnitude that how much velocity is increased. It is up to this much magnitude. So this much substrate increase leads to this much velocity increase. Okay, why? Because after certain point, more substrate is available, which had become easier task for the other substrate to bind with the enzyme, right? So because of that, there is sharp rise in the graph is seen. Now you may ask that why at the end it is become flattened. The reason is that beyond certain substrate concentration, all the enzymes is saturated with the substrate. There is no any binding site available, right? So if you go on adding substrate concentration, still velocity will not increase as all the enzyme is saturated. So this sigmoidal shape, this sigmoidal graph is the hallmark feature of the allosteric enzyme. Now if it is a non-allosteric enzyme, this V0 versus substrate concentration graph we had seen earlier in one of my previous video, and in case of non-allosteric enzyme, the shape is going to be like this. This is the hyperbolic curve, and it is seen in case of non-allosteric enzyme, whereas this sigmoidal curve, it is seen in case of allosteric enzyme. So if you want to find out that particular enzyme, is it allosteric or not, then you can simply measure velocity with various substrate concentration, draw out this graph. If it is sigmoidal graph, then it is allosteric enzyme, and if it is a hyperbolic curve, it is a non-allosteric enzyme. Now let us look at some selected examples of allosteric enzymes. In pathway of glycolysis, there are two enzymes which are allosteric in nature. The first one is the hexokinase, and second one is the phosphofructokinase. This hexokinase has only one allosteric site, and that is a inhibitor site. And with this allosteric site, this negative allosteric modulator is there, and that is glucose 6-phosphate. So glucose 6-phosphate acts as a negative allosteric modulator. It binds with the allosteric site of the hexokinase and inhibits the activity of hexokinase. In case of phosphofructokinase, it has both the site, inhibitor site as well as activator site, and its negative allosteric modulator is ATP, and positive allosteric modulator is adenosine monophosphate and adenosine diphosphate. Now in case of gluconeogenesis, there is one enzyme, that is pyruvate carboxylase. This pyruvate carboxylase has only one allosteric site, and it is an activator site. And with this activator site, positive allosteric modulator acetyl coenzyme binds, and it stimulates the activity of this enzyme. So this is about allosteric regulation. Now one very special type of allosteric regulation occur, which is called as a feedback inhibition. Remember, feedback inhibition is different than the feedback regulation. Here we will talk about the feedback inhibition, not about feedback regulation. But at the end of this lecture, I will tell that what is actually the difference between this feedback inhibition and feedback regulation. So let's first discuss about this feedback inhibition. See what happens. In our body, there are so many metabolic pathways are there. And metabolic pathways are nothing but a series of reactions. So let's say A is converted to B, B is converted to C, C is converted to D, and D is converted to E. These four series of reactions occur. This reaction catalyzed by E1, E2, E3 and E4. These four enzymes are there. Now what happens in the metabolic pathway, this final product, in this case it is E, this final product allosterically inhibits some of the earlier enzyme. So let's say it is allosterically inhibit this enzyme E1, which is the first step. But it is not necessary that it is going to be first step. It can be any of the earlier step. So here this final product E is allosterically inhibiting this enzyme E1. So such type of inhibition is called as a feedback inhibition. and this represents real cellular economy. Why? See, suppose this pathway is working continuously, then what will happen? This final product will be accumulated. But because of this feedback inhibition, what will happen? This final product will inhibit this earlier step, and so the formation of this final product can be stopped. Once final product is consumed by other pathway for other purposes, then this final product concentration will decrease and this inhibition will be lifted. So once again this pathway can be activated. So useless production of this final product, or you can say accumulation of the final product, can be prevented, and so our resources will be properly utilized. So this represents actually a real cellular economy. Let's look at one real life example of this feedback inhibition. In the pathway of pyrimidine synthesis, it is a multi-step process. So at the end of multi-step process, the final product, that is cytidine triphosphate, is synthesized. And as a part of earlier enzyme, there is aspartate transcarbamylase. Aspartate transcarbamylase. So this CTP, that is cytidine triphosphate, which is being a final product, it allosterically inhibit this aspartate transcarbamylase. So by this unnecessary CTP cannot be accumulated in our body. So this is how feedback inhibition works. Now let us look at this feedback regulation. What is feedback regulation? See, feedback regulation, it is actually a phenomena of control system. See, feedback regulation has many different types, and one particular type in which it represents one very specific mechanism, it is feedback inhibition. So feedback regulation can be of many different types, and one type is feedback inhibition. So we can say that all the feedback inhibitions are feedback regulation, but not all the feedback regulations are feedback inhibition. Okay, remember, feedback inhibition is very narrow term and it represents one specific mechanism, that is this one that we had just talked, whereas feedback regulation is very broad term. Okay, it is a phenomena of control system. Suppose, to understand more about this phenomena of the control system, suppose what will happen when there is increase in the blood glucose concentration. What will happen? This increased blood glucose concentration, it will lead to increase insulin secretion, and because of this insulin secretion, this blood glucose concentration will be brought down. So as you can see, this glucose will come back to its normal range. Okay, so this entire mechanism is called as a feedback regulation. Okay, but such feedback regulation is called as a feedback inhibition only when the final product inhibits, and that too allosterically inhibits, earlier step enzyme. Then that particular type of feedback regulation is called as a feedback inhibition. One more example of feedback regulation: if in our body temperature increases, what will happen? The hypothalamus senses that temperature is increased, and hypothalamus works on the body system to bring down temperature. So here also temperature is controlled by the feedback, that it gets input and it provides the output, so that particular system comes back to the normal, right? So this feedback regulation is one larger term. It is actually a phenomena of the control system, whereas feedback inhibition is a narrow term and it points or it directs us to a specific mechanism. Okay, so that is a feedback inhibition. So with this I complete allosteric regulation, and along with we had also talked about feedback inhibition. I hope that all the concepts are clear. If you have any query or confusion, please write it down in the comment section below. Thank you.